Imagine a medical marvel, a drug that literally changed the course of a fatal disease. That's what Ritonavir was in 1996. By 1998, 75,000 HIV patients were taking it daily, transforming their condition from deadly to manageable. Its power? Simple. Capsules designed to dissolve in about 30 minutes, ensuring proper absorption. This process was rigorously checked, with 240 consecutive batches passing without a single hiccup. It was perfect. Until it wasn't. Because then, something truly unfathomable happened, revealing a mind-bending truth hidden within the very molecules we rely on. An unusual observation surfaced that stopped everything cold. A single capsule failed to dissolve correctly. That one failure triggered an emergency shutdown, an entire batch destroyed. But the next day, the failure repeated. What they found inside was astonishing, horrifying even. The capsules were filled with a white, cloudy paste, teeming with millions of tiny, previously unseen needles. These weren't supposed to be there. These were new crystals. And alarmingly, even Ritonavir synthesized freshly in the lab yielded the same cloudy, compromised result. This wasn't a localized issue. Within a week, the Chicago factory ground to a halt. In a desperate move, production was shifted to Italy. Initially, all pills there passed their dissolution tests, offering a glimmer of hope. Yet, within mere weeks of Chicago scientists visiting, Italy too began experiencing failures. This indicated a complete, catastrophic contamination across all sites within 5 to 6 weeks. The cause, the detection, the prevention, the eradication, it remained a terrifying unknown, an unpredictable threat to astonishing drug. It was a molecular coup, silent and devastating. This baffling crisis wasn't entirely unprecedented. It echoed a 170-year-old scientific debate between giants, Justus von Liebig and Friedrich Wöhler. They were grappling with silver cyanate and silver fulminate. What made their debate so profound? Despite having identical atomic compositions, one silver, one nitrogen, one oxygen, one carbon, these compounds exhibited drastically different properties. One was explosive, the other wasn't. This led to the groundbreaking discovery of isomers, molecules with the same atoms but arranged differently. Scientists observing Ritonavir's white paste also saw spectral deviations. This meant a slightly altered bond arrangement, a subtle shift with monumental consequences. The answer, they realized, lay in something called polymorphism. Think chocolate. Cocoa butter forms different crystal structures, form IV and form V, and crucially, these affect its texture and melting point. That shiny, perfectly snappy chocolate we love? That's form V, melting around 34 degrees Celsius. The dull, crumbly kind? That's form IV, melting at a mere 27 degrees Celsius, requiring precise tempering to avoid. But for Ritonavir, this wasn't temperable. The new form, identified as Ritonavir Form 2, was substantially more stable and, crucially, less soluble than its life-saving predecessor, Form I. This new form prevented proper dissolution, rendering the vital drug utterly, completely ineffective. It was a molecular coup, mirroring something else terrifyingly familiar. Tin pest. Normal tin at below 13 degrees Celsius transforms into a less dense, gray allotrope, causing rapid expansion and structural disintegration that spreads like an infectious disease. Ritonavir Form 2 wasn't just a new form, it was dominant, unrecoverable. It had catastrophically seized control of a vital medicine. The very structure of its molecules simply changed, exposing a brutal truth. Even the most stable compounds can harbor an invisible vulnerability, fundamentally altering their destiny.